words of the day are stable equilibrium and unstable equilibrium, aka if this is up, how long will it stay up? So, if is it up? Is it in equilibrium or will it fall over? As you remember from the last lecture, if the center of mass is over the base or over the support points, this will not happen to you. Moral of the story, practice walking in high heels before you try it on the catwalk, or you will find that your base is so small it's practically impossible to keep your center of mass over it. If the center of mass is over the base, or at least between two support points, it will stay up and you will be in equilibrium, not a Japanese pop star caught in epic fail on YouTube. If you're trying to keep your center of mass over the base, not like this hockey player or something, what should the base be shaped like? Should it be small, like the tiny blade of a hockey skate, or rather, should it be large? We're going to go with the large. If your base is very large, then if your center of mass is anywhere from here to here, it will be over the base, or at least in between two support points, as it is now, and you will be in equilibrium. You will stay up. Let's start with the assumption that you are up. You are balanced. You are in equilibrium. Your center of mass is in the right place, over the base, at least for the moment. Gravity will do the work to knock it over. All you have to do is give it a little nudge. What does this look like? This is the configuration that you would call top-heavy. A top-heavy object generally means that if you give it the tiniest little push, gravity will do the work and knock it over. It may be in equilibrium now, but if you so much as breathe on it, it will fall over. It may stay up, but it is unstable. This pen is in unstable equilibrium. All I have to do is twitch, and it will fall. The silly Japanese pop model on the catwalk was in unstable equilibrium. She was standing up in those heels, but not for long. Now, for the next example. Draw this in your notes. Now, for the next example. Draw this in your notes and see where the center of mass is. More importantly, see which way the center of mass moves when you tip it.
Does it move left, right, or left or right, but more importantly, right and right? Watch that again. Which way does that center of mass move? The side moving to the right. Think about it. That's right. It moves down. This is our case called unstable equilibrium. Notice, unstable equilibrium is the case where, when you push it, the center of mass moves down, in addition to moving left or right. Where was the center of mass before it moved down? Well, logic says that most of the time that if it moved down, then it used to be up. We associate unstable equilibrium typically with a high center of mass. Why? Because down is easy. Gravity goes down. Who will do the work to knock it over? Gravity will do the work to knock it over. You push it, and gravity says, ooh, down, I can do that, and down it goes. High center of mass means gravity will do the work to knock it over. We call this top-heavy. If you give it a little nudge, gravity does the work to knock it over, and down it goes the rest of the way. Unstable equilibrium is still at equilibrium. It's still stable. It still balances. But it's hard to get to. And even when it does balance, it doesn't balance for long. Give it one little nudge, and it's down. Again, the definition of unstable equilibrium is not top-heavy. Top-heavy is our description. If it's top-heavy, look for where the center of mass is. If the center of mass goes down when you push it, that's unstable equilibrium. Ready for our next example? Here's the next example. Now we're going to stand the wine bottle the right side up. Locate the center of mass, give it a push, and see which way the center of mass moves. Left, right, and what else? Last time we were looking for right and down. What do we see here? Check it out. The center of mass unquestionably moves up. Is this a natural occurrence? No way. Wine bottles do not float like that. In fact, the only thing that could tip this wine bottle over this way is you, of your own volition, doing it on purpose because you're about to pour the wine into a glass. We call this stable equilibrium. Stable equilibrium is what you get when, if you push it, the center of mass goes up in addition to going left or right. Push it, and you actually have to raise the center of mass in order to get it to go that way. Well, if you push it and it goes up, logic dictates that originally it was down. Stable equilibrium is associated with a low center of mass. Because the center of mass is so low, and the only place for it to go is up, you will have to do the work to knock it over. Gravity will not apply. Gravity does not go up. Gravity goes down. If you push it, the center of mass goes up. Gravity will bring it right back down. If you give it a little nudge, not only will it not fall over, it will actually self-correct. Check it out. This water bottle has a much lower center of mass spin than the pen did when balanced on my finger. If I give it a nudge, it doesn't fall over. It stands itself right back up again, exactly as if I hadn't pushed it at all. Now, granted, if I try hard enough, if I actually do the work, I can knock this thing over. But if I'm not trying, if I'm not actually doing the work myself, stable equilibrium self-corrects. The center of mass is low, so if I'm not bodily lifting this up myself, it's not likely to go anywhere. There are three types of equilibrium. We've discussed stable equilibrium with a low center of mass. Unstable equilibrium with a much higher center of mass. There's a third type of equilibrium. The third type is neutral equilibrium. Can't knock over what's already down. If any push will keep the center of mass at the same height, no work will be done at all. You can't knock it over. There's no up, there's no down. There's only a flat, level table. This is neutral equilibrium. It doesn't fall over as easily as unstable equilibrium, but it doesn't self-correct like stable equilibrium either. It doesn't fall over, but doesn't go back to where it was before either. Now, examples. All the labels have been taken off these bottles of wine. Which one of these was the $50 bottle Prix-Hagafen, P-R-I-X, which is the California wine that they serve at the White House when they're entertaining Israeli dignitaries and they need kosher wine? And which one of these is the $4.99 bottle of Rashi served at Kiddush at your local synagogue, which also can be used to strip paint off cars and be used as coolant in your carburetor? Which one of these will the sommelier burst into tears if it is spilled, and which one would you might want to spill anyway to save the drinkers the unpleasantness of drinking it themselves? Pause, think, take a few sketches, draw a center of mass, which way is it going to go, and decide in the end. Ready? It's not just the green bottle. Check it out. This bottle has no glass at the bottom. The center of mass is closer to halfway up, maybe a little less than halfway up because this neck is so thin, maybe it's around here. But if you push this bottle over, the center of mass is going to go down. These bottles have a huge, thick, heavy mound of glass at the bottom. The center of mass is much lower because of all this glass. And if you push that bottle, that center of mass is actually going to go up. The bottle will wobble, but it will self-correct. It will keep itself up, and it will not spill the wonderful, delicious, fine quality, amazing wine with that lovely bouquet that you spent so much money to buy. Consider your drinking glasses at home. Go to the kitchen cupboard, open, and take a look at your family's good drinking glasses, the ones that your parents got as wedding presents and are still around. If you're doing this out and about at your local Starbucks, check out the drinking glasses used at the diner at the restaurant across the street, where they buy them in bulk by the hundreds and don't want to reorder. Look at the bottom of the glass. What do you see? I'll bet you anything you see a thick, heavy bottom. Not in the same shape as this. There's a lot of glass in the bottom of that good, solid, I don't want to have to buy another one drinking glass. Compare that to the paper cups at the Starbucks or the plastic cups down by the water cooler, and you'll notice no one cares whether we spill them or not. We do not have that thick, heavy bottom to bring the center of mass so much lower. Now, it so happens that the other purpose of this big mound of glass, the reason that it's round here and not flat like the drinking glasses at home, is so that the dregs of the water, the sediment, can settle around the bottom in a circle, and you can pour out the fine, clear wine from the top. If this also means the bottle is less likely to spill, so much the better. Let's try this with architecture rather than home design. This is the Seattle Space Needle. It is a gorgeous work of modern building. It basically looks like a hamburger on a stick. Draw the Seattle Space Needle in your notebook, as you can see it, with a big, heavy observation tower tourist trap and restaurant at the top, surrounded by sky, supported by what looks like 4 relatively thin spindly legs, and a base that is no bigger than the top. If anything, a little bit smaller. Draw this exactly as you see it. Pause, mark the center of mass, and draw your little arrows. If the center of mass is fairly close to halfway up, you knock this building on the side by a strong wind, the kind they have in Seattle, called the Emerald City because it rains practically every day of the year and all the grass is green. Which way will that center of mass fall? Pause, draw, identify the top. Did you get the center of mass? Roughly in the middle is going to go down. I did. And now we ask the question, what benighted civil engineer in the city of Seattle ever allowed this design past the planning stages? This looks like a disaster waiting to happen. All it takes is one strong wind to blow the building. Next thing you know, gravity knocks the whole thing down, flattens several blocks of downtown Seattle, and probably being the last thing that anybody in the top ever sees. This is terrible. This is ridiculous. This is stupid looking. I don't care that it looks gorgeous. I don't care that you want a building that looks like a hamburger on a stick. It's not going to stay up in a strong wind. Now, let's try some logic. This building was approved. This building was built for many years in the 1960s and has stood safely in the strongest of hurricane winds coming off the Pacific coast ever since. I submit to you that the center of mass cannot be over here where it appears with the naked eye. There must be something else to this building. So let's try to work out what we could put where to make this stay up. Please note that there are very clear sight lines around this building. There are no guy wires over here that can be seen with the eye. There's nothing over here except more apartment buildings and roads. In your note, decide, if the center of mass is not safe to be up here, where would you want it to be? And where would you put a lot of extra mass on different structures to move the center of mass where you want it? Draw this in your notebook and bring it to class tomorrow, where we will discuss